Hello, someone just stop the recording. Yeah. Okay. So 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 we had up to 16. Today's 17, I guess. Don't remember. Yeah, 17. Today is 15. Okay. So remember that we had represented every molecular orbital as a linear combination of atomic orbitals. And I said that these atomic orbitals form the basis set for the molecular orbital calculation. And I just mentioned also that these basis functions are usually taken to be Gaussian functions. So today we will talk about the details of this and why we chose Gaussian functions and why not some other functions, etc. So in principle, any infinite set of functions can be a basis set. So you have the Fourier functions, which are commonly used as a basis set for expanding oscillating waves or oscillating functions of different kinds. Then you can have a polynomial basis set. You can have a Gaussian basis set, as we will talk about today. You can have a sine and cos functions as basis sets. You can have many things. But for an atomic orbital in particular, we have an idea about what it should look like because we know the hydrogen atom solution. So the solution for the hydrogen atom, it looks like, so let's say the 1s orbital of the hydrogen atom, that has some constant, and there is e to the power minus alpha r. So this is what the 1s function of the hydrogen atom looks like. This is the simplest function that we know, and this is the exact solution of the Schrodinger equation. So this certainly looks like this. Okay. And so since this is a spherically symmetric orbital, the angular parts are not there. We're talking about the s orbital, and I will stick to s orbitals today just to keep the expressions simple. Anyhow, I just want to illustrate the principle, so it's not necessary to write these things in detail. And so functions of this form, which is an exponential with a negative sign, are called Slater functions. So we know that atomic functions or atomic orbitals are Slater functions. They're also called Slater orbitals or Slater type orbitals. Okay, and in general, so this is for 1s in particular. If I want a general function, say a Slater function that has an exponent, and these are the two vectors. So r is the variable, and Ra is the so A is the atom on which this basis function, for which this basis function is defined. So for atom A, and this looks like some constant which may or may not depend upon zeta. So we have some some function of, is this called zeta? No, this is called xi. Sorry, xi. This is some function of xi, and you have e to the power minus xi r minus ra. So that is the definition of a Slater function centered on atom A. This is a Slater function centered on atom A. Ra is a constant vector. R is the variable. Xi is the parameter, which tells me how the function behaves. So if this is R and this is phi ASF, a Slater type orbital looks like this. It is simply an exponentially decaying function. And how fast this decays is controlled by xi. So let's write the Slater function for a 1s orbital in general. So not necessarily hydrogen. Then it looks like it's a function of xi and r minus ra. And this looks like xi cubed by pi to the power half e to the power minus xi r minus ra. Okay, so so over here, since this is always decaying, we put a modulus over here. So it depends uh, on the distance from the atom A and not on the direction. Because if I did not put a modulus here, my s orbital, for instance, would decay on one side but not on the other. So you don't want that. You want a spherically symmetric function for the s orbital. So this is a modulus. Fine. So this I know is what the hydrogen 1s orbital looks like, or and this xi is different if we are talking about a 1s orbital of a different atom, a different type of atom. Okay, but the more commonly used basis function is a Gaussian function, which looks like this. There is only a slight difference, but it makes a lot of difference to our numerics. So that's why instead of Slater type functions, we use Gaussian type functions. So that is the only difference. Okay? That instead of decaying linearly with xi, the Gaussian function decays with decaying linearly with the distance from the nucleus. The Gaussian function decays quadratically. So what difference does that make to what it looks like? So I'll draw it on this function itself. So this will look like something like this. So let's say this is phi A, and this is the Slater type function, and this is the Gaussian type function. So the two major differences in these two plots is that here at atom A, at the nucleus, you have a finite slope for the Slater function, but a zero slope for the Gaussian function near the nucleus. And near the tail of the function, you have a slower decay here. So this is slower decay for the Slater type function and a faster decay for the Gaussian type function. So, uh, so if you have a Gaussian function, then the area in which you need to integrate numerically is smaller because it decays faster. And for the Slater type, you will need a much larger area in which to, area or volume. I should keep saying volume, I guess, because this will be a 3D picture. You need to integrate a larger volume for the Slater type function and a smaller volume for the Gaussian type function. Also, you may have encountered this, that when you have a very high slope in a small area, it causes numerical difficulty in integration. So this is like the problem of integrating a delta function numerically. So this is difficult. So that is also easier with the Gaussian function, that you don't have a sharp peak in a small area. It is a rounded picture. So these are the two advantages from the point of view of simply the nature of the functions. But there is also, in particular for our Hartree-Fock calculations, there is an additional advantage. So what is the additional advantage? So the most expensive part of our calculation in Hartree-Fock is the evaluation of these four center or four index mu, nu, lambda, sigma. So these four index integrals are the most expensive part of our calculation. So this is the spatial integral. So what do they look like? So they look like phi mu star, phi mu, R1 to inverse, phi lambda star, phi sigma, dr1, dr2. So remember, this is the notation for the spatial integral from the Mulliken notation. So that's why this is star, unstar, star, unstar. Okay. Now these basis functions can in principle be on four different atoms in a molecule. So if a molecule has more than four atoms, then each of these basis functions can come from different atoms. So let's say mu comes from A, nu comes from B, lambda comes from C, and sigma comes from D. So this is A, B, C, D. So this integral, as it is spread over a very large space. So my integration volume is very large. On the other hand, this is also so this will become very expensive, because you will have to traverse the full region that these four basis functions cover. But if my phi mu and phi nu, phi lambda and phi sigma, they are Gaussians, then the property of a very easy, no, let's say, and a property of the Gaussian makes this simpler. So what is this property? The property is that the product of two Gaussians is another Gaussian which is centered on a point between the two original points. So if I have a Gaussian function of the 1s orbital with an exponent alpha which is centered on atom A, and I multiply that with another Gaussian function which has a different exponent beta, and is centered on atom B, then this product can be written as a third or a different Gaussian, which has a different exponent and is centered at a different point. And this can be multiplied by a constant which depends on the two atoms. And the expression for K and P, they are known analytically. KAB is equal to 2 alpha beta by alpha plus beta into pi to the power 3/4. So this is just a number which can be evaluated, and e to the power minus alpha beta by alpha plus beta into just the internuclear distance square. And you also know P. So the exponent of this new function P, that is simply alpha plus beta. And the other thing that you need to know is, of course, where this new Gaussian is centered, that is Rp. And Rp is simply a point which lies on the line joining A and B. Okay, and this point is placed such that it divides the line in the fraction A's to B. So if you remember your vector algebra, then this is the formula which uh, tells you the point which divides the line between A and B in the ratio alpha is to beta. So alpha is to beta are the exponents of the two Gaussian functions. So this property of the Gaussian can be used to great effect in evaluating this integral. So let's look at the two stars. So you can have okay, now so I have put the stars here. Now if you open Zava and Oslund, you'll see that they have done away with the stars. Why is that? Because all the basis functions are constructed real. So the basis functions are constructed as real. However, when you solve the Hartree-Fock equation, your molecular orbital can have complex coefficients. So C's, which are the combining coefficients of AOs in an MO, they can still be complex. In fact, your MOs can also turn out to be complex, and then you can recombine them to be real. So I don't know if you have heard of this before, but you can have the p orbitals. When you solve for them, they can, even for atoms, are complex, and you get something that is p plus, p minus, and p0, even in the hydrogen atom solution. And these are complex. But then you combine them to give you px, py, and pz, and they are real. So this can happen in general for molecular orbitals also. However, when you start out, the basis functions are taken to be real, because for complex functions you don't have any intuition, and finding out the integrals in complex basis is also uh, about 8 times more expensive for every 4 index integral. And fine, so they are real, so they have, so you can do away with the stars, and you have mu a, mu b, lambda c, sigma d, that is phi a, phi b, phi c, phi d. This is mu lambda sigma dr1 dr2. And let's say I apply the product rule on A and B and C and D, then this AB will give me KAB, the constant, into and C and D will give you the CD constant, and I will have phi. So what I wrote it as phi 1s, okay, phi some Gaussian function P R1 minus RP into phi some other Gaussian function Q R2 minus RQ integrated over dr1 dr2. So what has happened? So I had a 4 orbital integral which I have reduced to a 2 orbital integral. And then this becomes much cheaper. So this becomes as cheap as doing a 1 electron integral or or the small h, the 1 electron part of the Hamiltonian. So this becomes much cheaper. Sorry, when I missed R1 to inverse. Okay, but the question still remains that the two functions, the Slater function and the Gaussian function, they are fundamentally quite different. So do the Gaussian functions represent the atomic orbitals sufficiently well for us to get accurate numbers? So for that, if you plot a single Gaussian and a Slater orbital, you will see that they do not. They are quite different. So I can try to draw something roughly. So if I draw the just the 1s Slater function, it gets a little bit faster, so it looks something like this. I'm not can't draw this well on this tablet. 1 minute. So yeah, okay. So this is what the 1s Slater function looks like. And the Gaussian function with the same exponent will look like this. So that is quite a bad fit. You can, let's say I let my exponent be a variable and I try to find the exponent for the Gaussian such that it such that the difference in the two functions is as close as possible. So we are doing a least square fitting, let's say, with the variable being the exponent of the Gaussian function. Even in that case, you can at most get to something like this. So when you try to improve um, the close part or the near nucleus part of it, the tail becomes worse. So with a single Gaussian function, it is not possible to represent a Slater function very well. So what is done is that you allow a Slater function to be described by again a combination of Gaussian functions. Okay, so instead of taking a single Gaussian function, instead of one Gaussian function for one Slater function, we take many Gaussian functions for one Slater function. And we take a linear combination which looks like this. So I have taken L number of Gaussian functions. Yeah, so P Gaussian function. Sorry, this is the Slater. So I'm trying to represent the Slater function as a linear combination of Gaussian functions. So this is a Gaussian function for the muth Slater function. So that's why I'm carrying the index mu here. And alpha p is the exponent of so you have alpha 1, alpha 2, alpha 3, etc., which are the exponents of the first, second, third Gaussian functions, which have a combining coefficient of dp mu. So let me just write it for a particular example that will make it clear. So d1 1 phi 1 alpha 1 sorry 1 mu alpha 1 mu minus RA plus d 2 mu phi 2 Gaussian function alpha 2 mu minus RA plus whatever d L mu phi L alpha L mu R minus RA. So this is one Slater function centered on on the atom A, which is represented by many Gaussian functions. So this is so I'm trying to represent the Slater function, and when you combine the Gaussian functions, then this is called a contracted Gaussian function. So when you take a linear combination of Gaussian functions, it is called a contracted Gaussian function, and a Slater function can be represented with a contracted Gaussian function. And now we have more variables which we can optimize. So now we can optimize both this and this. So we have two types of fitting parameters. And this allows us to describe the function better. In So with a suitable choice of both d and alpha, you can find out a function which represents your atomic orbital as best as you would like. In principle, you can do it as well as you would like by taking more and more Gaussian functions and more different types of exponents. But usually, up to just taking up to 3 is good enough. So from this principle comes the names of the basis sets. So you have STO1G, which is Slater type orbital, where each Slater orbital is described by one Gaussian. So this is a Slater type orbital, and G is equal to Gaussians used to represent it, and this is the number of Gaussians. So let's say I call this N, then it's STONG. And the most common ones that you will see in the lists in packages: STO1G, STO2G, STO3G, 3G, and STO6G. This is quite rare. This is good enough. And this is very bad. Okay. So this is the most common, where every Slater type orbital is represented by a linear combination of 3 Gaussian orbitals, which means that there are uh, 6
Hello, ma'am.
fitting. Yeah.
Can you repeat, madam?
Yeah, sure. Can I repeat from where?
STO1, what is that?
Yeah,
NGO that
so
is.
STO1G. Okay. So I want each atomic orbital to look like a Slater function. So they are called Slater type orbitals, which we are representing by means of linear combinations of Gaussians. So the names that you will encounter is STONG, which means that every Slater orbital is represented by a linear combination of n Gaussians. So when it's STO1G, it means every Slater type orbital or every atomic orbital is represented by one Gaussian. That which we saw was quite bad. Or you can have a linear combination of 2, then it's STO2G. If you're a linear combination of 3, then you have STO3G. And if you have, so let's say for STO3G, you will have 3 of these. So you will have at least 6 fitting parameters. And these fitting parameters are predetermined for every atom type. So an STO3G basis set for a hydrogen atom will have 6 numbers, 3 of which are the combining coefficients and 3 of which are the exponents. And similarly, for let's say a lithium atom, you will also have 6 parameters, but the values will be different. They will, okay? And how do you find out these values? So to find out these values, you basically take the least square fitting of the Slater orbital you want to represent with the Gaussian. So either you minimize the least square difference. So how to find fitting parameters? you minimize the difference of the two functions in a least square sense. So mathematically speaking, if you have an integral over all space of the difference of a Slater type function, okay, with some parameters, and the contracted Gaussian function with the with again some parameters, okay, the difference squared. You want to minimize this, okay, and you can do it for any two functions that you want, but normally you would specify the exponent of the Slater function, which you have to do specify. This is your known function, so to speak. So you know the function entirely, including the exponent. And in the contracted Gaussian function, you fix the exponents. So for a fixed set of exponents, okay, I can also call this zeta. Let's say you start with the same thing. So you fix the exponents and then you optimize the coefficients. So you fix the alphas here and you find the d's. Then you can change your alphas and again find the d's, and this is also again an iterative procedure till you get your desired level of similarity between the two functions. This is a very, very tedious job, and there are research groups who are dedicated to finding basis sets for various atoms, and they've been doing it for years and years and years. And this is, and I don't know, I just read this from Szabo and Oslin when I started doing research, and I decided then and there that this was any research group which does this, I am not going to join it. But maybe some of you might find it interesting. I don't know. Anyway, so but this is a very, very important job. Okay, so you should not look down on them. They're making things easy for you. So they find these coefficients for you, optimize them, find the quality of wave functions, and then they put up these exponents on a freely available website, and we simply copy these basis sets from there. Or quantum chemistry packages, they download these basis sets and feed them into their package, so it's easily available. Okay, so and you can't do anything without these. So they're very, very important. That's where you start your calculation. And if your basis set is bad, whatever level of theory you do, however sophisticated, your answer will be bad. Okay, so it's a very, very important job, but to me it seems a very boring job. Okay. So I really am grateful to those who are doing it for us. Anyway, and the principle is to minimize the difference, and in effect it means to maximize the overlap between the two functions. Okay. So you maximize the overlap or you minimize the difference, and you do it iteratively till you get your set of fitting parameters. Okay. The other important thing is that eventually you need your basis functions to be normalized, remember. So after you have, so at every stage you must ensure normalization. So there. So you need to know how it is done, but you don't need to work it out, because as you can see, this is not something you can just do on pen and paper. You will need a code for it and a tremendous number of calculations to finally get there. And okay. And okay, also note that this is only applicable to the radial part. So we are just describing the, so this whole procedure of basis sets tell you the radial part of the function. So what about the angular part? So the angular part is decided by what are called spherical harmonics. Just knowing the name is more or less enough. So these are the angular functions, and the angular part is multiplied. So this is multiplied in addition. So the whole numeric procedure acts on the radial part. Also because the integrals are only dependent upon the radial part in a way. The angular parts, so they're on R, right? The integrals are on R. So the radial parts, and it's on the R vector. So the angular part is there. But if your basis functions have only the radial part, then the numerical part of the computation is restricted to the radial part. The angular part can be analytically done in most cases, I think. So I don't have any hands-on experience in this part of the thing. But as far as I know, it is quite a laborious and difficult part. But it is already done. That is the good part. You don't have to, almost no one today has to code any part of this unless you're developing something from scratch. So the integrals are readily available in most cases. Of course, if you develop new functions, like new basis functions, you will have to develop the machinery to do the integrals as well. And then you will have to learn more about it. Yeah, and if you want to have a look at basis sets, if you want to see what basis sets look like, then there is the, what is it called? EMSL, basis set library online. So I just show it to you for now. Let me see. I will have to stop broadcasting, or can I? No, I can just search for it. Okay. So this is the Basisset Exchange.org. Okay, it used to look a bit different when I last looked, but okay. And there you have the periodic table, and say you want the basis set. Say your molecule is magnesium chloride. Okay. So then you can have you choose magnesium. Okay. Then you have to choose the format. So let's say in your assignment we have used GEMS US. And then you say, where is the choice of basis set? Where is that? Is it no? Okay. It looks different now. 1 minute. So where is the type of basis? Okay. So I have to search then maybe CSTO. Okay, 6 basis sets. So where are the basis sets? Can someone see? So the format has changed. Now I cannot find the.
Maybe trying desktop site may help.
Yeah, but I'm on a tablet, so I.
No, I'm saying change it to desktop site.
Okay. Is there an option on the website here? It's not there.
Option of Chrome, at least I know about Android.
Strange. Okay. So this blank thing. So somehow something is not appearing. Okay. So see, you have the options here. So let's say I want STO3G, the one which I said is best. Then it tells you which atoms have STO3G basis sets available. Then let's say I want magnesium. Okay, so it tells you STO3G minimal basis, 3 functions per atomic orbital, which means 3 Gaussian functions which are contracted to give you 1 function. Okay, then I say the package I want the format to be compatible with is GEMS, and then I say get basis set. So then it looks, so the basis set will look like this. So you have the magnesium atom. This is the first s orbital. So the innermost core orbital of magnesium, the 1s orbital, it is represented by 3 functions. So this 3 is there to help the code know like how many functions to read after that. So 1, 2, 3. So the first function has an exponent which is 0.299 into 10 to the power 3, and the no wait, let's see which one is the contraction coefficient. So according to the format, yeah, I think the exponents. Yeah, so the exponents are the first number. Okay, the first number is the exponent, and the second number is the combining coefficient. So it's 0.299. So it's minus 0.299 into r squared function, and it has a combining coefficient of 0.154. Similarly, there is a second and there is a third function, and these 3 together represent my 1s atomic orbital of the magnesium atom. Okay. Then after 1s you have you should have 1s, 2s, 2p, 1 minute. One S and 2S. And then this is. I'm not sure why they have an L here. This should also be an S type. Magnitude is 12. So 1s2, 2s2, 2p6, 3s2. So I should have every, so 1s2, 2s2, no, that will not work. This is, okay. Data from Gaussian 9. I think this is not the GMS format that I am used to. So let's look at a simpler one. I don't know why. This is strange. So GMS normally it is SPD. That's how they write it. But here they're writing something like L, which is confusing me. 1 second. So what is L? It used to be just the EMSL basis set library, and now they have made some sort of collaboration. So let's see. So for lithium, you have 1s and then 2s, but then they say it's L. Why do they say what is L? I think it is, they have changed some sort of format maybe. Look at this one. Okay, I'm sorry. Okay, I'm not sure what the L here is. Okay, the S, normally it is like SPD. For some reason, they're saying L now, and I'm not sure. I will look into it and tell you again in the next class why it looks different. So, but anyhow, the point is that the basis sets of the various atoms at various levels of accuracy, they're available online. They're also available inside all the quantum chemistry packages, and you can use them in your calculation. And what we spoke about minimizing the least square difference and also the finding out least square difference and or maximizing the overlap, that is the principle by which these are constructed. Okay, but of course there are more advanced techniques as well, and a lot of work goes into constructing these. As you can see, you need them for various atoms, and they must work well when you use them in various molecules. So actually, the Slater type orbitals, this STONG, you see they're called something like minimal basis. It means that that is the most intuitive basis that you can have. But also, if you do higher levels of theory, let's say if maybe you have heard of couple cluster theory or something like this, where you calculate the electron correlation, then again you have basis sets which are optimized to give you good results for the correlation. Can I type here? Okay, I deselect this. Can I? No, I can't type here. I'll show you this from the desktop. I think this is not working. So then there are different names, like they're called CCPVDZ, for example, is a basis, and this is called correlation consistent So other examples are, let's see, CPVDZ. This is a basis meant for computing correlation energy. So beyond Hartree Fock. So this is beyond Hartree Fock. And here it means CC is correlation consistent. P is uh, polarized. V is valence. D is double. And Z is zeta. So what do all these mean? So correlation consistent tells you that they are optimized taking into consideration correlation energy. So they will work well for you if you're doing correlated computations. Polarized means that there are higher order functions. So if you're describing a 1s Slater orbital and you're only using S-like Gaussians to describe it, it is unpolarized. But if you're using both S and like higher angular momentum orbitals, if you're also using P or D or F, they are called polarized orbitals. And when you do correlation energy calculations, then it's important to have these polarization components to give the orbitals flexibility to adapt to your correlation. Then V is valence. So polarized and valence go together. So it means that the valence orbitals are polarized. So the innermost core 1s, 2s orbitals, let's say, the ones which are inside and are not interacting much, they are still pure in the sense of S is described by S, P by P, and D by D. But the valence ones have higher angular momentum components, and double zeta, they go together. It means that there are two Gaussians per AO. So there it was called NG, remember, and double zeta again means the same thing. And equivalently, you can have a CCPVTZ. Okay. You can have an augmented CCPVDZ, for example, and this augmented means now that you have extra polarization functions, which means that the number of atomic orbitals uh, is it's not only the occupied atomic orbitals which have a basis function. You can have so there are empty atomic orbitals in the basis as well. Okay. So these are extra polarization functions. Anyway, so there is a huge variety of this. In fact, if you want to do property calculations, like for electric properties like dipole moment, polarization tensor, etc., then you have what is it called now? Slater basis. You have something called a Slater basis. And this is meant for electric properties. So that's why selecting basis sets is sometimes you will hear people saying it's an art and not a it's a science-based art, you can say, to design the basis function so that you describe what you want well. But in any basis set, if it's large enough, then you go to what is called the basis set limit, and then the properties or the energies that you calculate become invariant to the invariant. So a large enough basis whatever type it is will give you the same answer. But since you always want to minimize your computational effort, you take a well designed but small basis set. You take just enough. And whenever there is a balance involved, you see there is there is question of experience, background study, art, okay? But the good part of it is when we do computations, it is more or less well known which basis should be used for what purpose. So you don't necessarily have to look at the details. So the literature will tell you which basis you should be using, and you can go ahead and use it. But in case you are getting inconsistent results, then you should know at the back of your mind uh, that there could be a problem with the basis. For example, it is sort of experience that if you're doing DFT calculations, so many of you may have heard of it, density functional theory calculations, then basis sets which have names like 431G, 631G star star. Okay, this family is better for DFT. But if you're doing coupled cluster, etc., or perturbation theory, or what are called wave function based methods, so if you're doing wave function based correlation theories, then this family is better. And you can find the logic behind this if you look into the literature of how they were developed. But for most people, they don't need this knowledge, but they just need to know what is good for what. Okay, so don't get intimidated by this. So that brings us to the close of Hartree-Fock theory. You can read the chapter in Szabo, of course. It's a very, very big chapter. But you can just focus on what was taught in class. But it would be good if you go through it at least once, especially since they have done a proper numerical example for, I think, HEH plus, a full calculation about what the numbers will turn out. They have evaluated it. So that will give you a complete picture. And then if you can do the assignment, then you will know both how to do things by hand and how to do things um, in the way it is usually done on a computer. Okay. And for the second assignment, I just wanted to tell you that just because there are 2 weeks, don't wait till the end of 2 weeks, because it might be that you need some help in between, and then we need time to go through it. Okay. So if you start last minute, at least read the assignment and try it initially. And if you see that, okay, I can manage it at the end, then you can go and do it at the end. But at least go through it once. Okay. So I think I will stop here today. Wait, I wanted to give you a little classwork. Now I've forgotten the number of the exercise. 1 minute. It involved showing the property of the Gaussian orbitals. The fact that the product of two Gaussians is another Gaussian centered at a different point. Okay, yeah, this is so the classwork I wanted to give you was exercise 3.19. You can start now, we still have 8 minutes. And if you have any issues, we can deal with it again on Thursday. And from And we should probably have a quiz again next week. So I will talk to Professor Pal and then I will get back to you on WhatsApp. Okay? So I'm closing the class for today. So you can switch off the recording. Do you have any questions on basis sets? Anyone? Okay. So if there are no questions, then I will. I'm leaving the call. Okay. Thank you. See you again on Thursday then. Bye bye.